The specifics of what's going on here aren't too important, but what you'll see is there's a lot of mouse movements going on, there's a lot of actions being pursued, and this is showing a high level of multitasking being performed by a human in a game. And the question is, how do we build agents that can demonstrate this level of multitasking and really build systems that are doing tactical, strategic, and economical actions concurrently while still achieving a high-level goal? So you also see that there's micromanagement of individual units, so there's split-second per unit reactions being combined with a high-level strategy. So the structure of this talk is to first introduce multi-scale game AI and provide an example, specifically StarCraft. I'll then talk about related approaches for building game AI. I'll then introduce our approach specifically, which is reactive planning, then discuss idioms that we use to address these challenges, and then provide results of what our agent can perform. So the goal of this project was to build a StarCraft agent that can play at a competitive level against human opponents. And the foundation of this research was this project called Able Wargus, where we used a behavior language to build a complete game playing agent for Wargus, which is an open source clone of the game Warcraft 2. However, there's been a lot of research applied to Wargus, but it's quite simple when compared to modern RTS games. So what we wanted to do was scale up the complexity and apply this framework we had previously developed and find out where it really breaks. So at what level of complexity do we really have to rethink our architecture? So what we noticed is that StarCraft is much more complex than Wargus, and part of the reason for this is that similar to Wargus, you do need to have a high-level plan of what's going on in the agent. But at the same time, you have highly reactive per-unit behaviors that need to be performed. So there's much more micromanagement that occurs in StarCraft. And the problem is that you're doing highly reactive behaviors along with a high-level plan that needs to be executed. Additionally, individual units within StarCraft can take the role of many different goals throughout the game. So an individual unit might be used in a micromanagement scenario where it's pursuing an individual goal. It can be in a group behavior where it's actually part of a group achieving a goal, or more of a global goal of, say, attacking the opponent where instead of preserving its own self, it's going for the greater good. And one of the issues is that you can't simply just throw a layered approach at this where you do some sort of hierarchical structure, because there's contentions between different layers within this hierarchy. So an example is in-game resources such as minerals and best-paying gas, where different layers in your hierarchy might need to consume these resources. Another possible contention is units, which might be used for, say, scouting as well as combat scenarios. And there's also concepts such as map control, where you don't really want to build an expansion somewhere until you have some control of that region. So there's contention over this concept of control on the map. So we define multi-scale game AI as a system that concurrently reasons about multiple levels of action across multiple coupled scales. So you might be performing actions at strategic and tactical levels, and there's a coupling between those. An example of this is StarCraft, where in order to attack the opponent, you first have to build the units capable of attacking. So while you can simply build a hierarchy there, there's situations where the strategy manager might say, I need this unit to defend versus needing it to attack. So it has to take on different roles throughout the context of the game. So I also mentioned shared resources as being a contention for, you can't just simply throw a layered approach at this. And what you'll find out is there's domains which are non-hierarchically structured that could benefit from this approach, as opposed to, I'll talk about actually hierarchical situations in a second. So an example of this in StarCraft is an agent has to control vultures, which are units that are very fast, but they cannot take a lot of damage before they're destroyed. So within the context of an agent playing a complete game, it has to micro vultures. And within the context of a game, a vulture might take on individual goals, such as self-preservation. Later in the game, the vulture might participate in group behaviors, such as work harassments, where it actually becomes part of a squad that tries to run past a group of military units in order to get to the opponent's worker units. And to achieve this goal, it actually has to take damage, which conflicts with its self-preservation goal. Additionally, it might do aggressive mine placement, where it goes in and takes damage in order to place mines around opponent units, and this also conflicts with a self-preservation goal. And finally, it might participate in global goals, such as supporting the siege line of the agent, to where it's basically there to absorb damage so the more expensive units don't get destroyed. So common approaches for commercial game AI are finite state machines, subsumption architectures, and behavior trees. One of the generalizations of these approaches is they're mainly applied on a per unit basis. So each NPC will have a FSM or have a behavior tree. And one of the issues is that the mechanism for deciding when to participate in an individual or squad-based behavior is determined by some external component. So if you look at squad behaviors in Halo 3, Dami Nizla's work, he actually did a mechanism for assigning units to specific squads in a component that was external of the behavior trees. And what you have to do to build this using traditional approaches is some sort of abstraction boundary. But in domains where there's lots of competencies with cross-cutting concerns, these abstraction boundaries start to fall apart. So here's a famous facade slide, and the reason I'm showing it is because I am using Able in order to implement my agent. Able was first used to author the NPCs in the interactive drama Facade. I'm using it because it has several properties that make it excellent in a domain where you have concurrent goal pursuit across several levels of detail. And Facade is also an example of a multi-scale AI problem because an NPC has to perform actions at several levels of granularity, from low-level facial animations such as Grace and Tripp's eyebrows to trying to follow the high-level strategy of having a coherent plot. So my agent is built on behavior language, Able, which is used to author reactive planning agents. And as I mentioned, it enables integration of reactive parallel goal pursuit along with long-term planfulness. An Able agent has a decision cycle thread which determines when it expands its active behavior tree, which is a set of behaviors that can be selected for expansion. And this actually runs in parallel with the game logic thread, and it's a bit different than behavior tree style architectures where you select the behavior to execute and then scheduling is a separate problem. In reactive planning, you begin executing an action as soon as it's selected, and therefore it integrates the selection and execution logic of the agent. Able agents interface with the game world through the use of sensors, which update the agent's working memory. Actions are executed by the agent by performing physical actions. So I'm going to introduce some of the keywords that are used within our agent for some code snippets I'll show later. The first keyword is precondition, which is used to specify a set of conditions which must be true for a behavior to be selected for execution. And this is analogous to selector nodes and behavior trees. Or, that's what subgoal is. A precondition is simply a set of conditions that must be true. A subgoal selects a child behavior for execution, and it's essentially a selector node and a behavior tree. So you can specify a subgoal by name, and then behaviors matching that subgoal name will be selected for execution. And the highest priority behavior will be selected. Next up is spawn goal, which is similar to subgoaling, except that instead of expanding the node within the current thread of execution, you actually spawn a new thread of execution to pursue that goal. A mental act is a bit of computation that the agent can perform, such as updating its working memory. And a context condition is a special type of precondition, or it's a condition where it must remain true for the entirety of the behavior for the behavior to continue executing. So the agent I will be presenting is EISBot, which is the Expressive Intelligence Studio's bot, and it's one of the entries in the competition here. I've implemented it in the Able Reactive Planning language, and two features of it is that it partitions gameplay into specialties using the idea of managers, which were presented in the Able Wargus architecture, and it facilitates communication between these competencies using a Blackboard architecture. So to divide up StarCraft gameplay into specialties, I've identified the following competencies. There's strategy, economy, tactics, scouting, and base building. And these can be further broken down into specialties within these competencies, such as build order, which would be the opening strategy in the agent, army composition, which would be the concentration of units you want in your army later in the game, and then aspects such as defense, such as building countermeasures to what you've scouted from the opponent. At the tactical level, you might have several specialties as well, such as micromanagement harassment techniques or operations such as doing transport units to drop units behind an opponent's base, or larger scale attacks such as pushing the opponent's base. So where multi-scale really comes important here is whenever there's cross-cutting concerns across these competencies. So earlier I mentioned minerals and Vespene gas as something that's actually contended for between these different competencies. So the economy manager will want to build worker units in order to increase resource income rates. But at the same time, those resources will be needed by the strategy manager to decide which tech options to explore, so there's contention there. Another is map control. I mentioned you would need to actually defend a location before you build an expansion there, otherwise the opponent could simply destroy your expansion before it's useful. And also the concept of timing. So you can't have each of these competencies working in isolation because they won't actually produce a strong assault. So an example of this in StarCraft is timing attacks, where the player first positions an army in front of the opponent player's base, waits for an upgrade to complete. As soon as the upgrade completes, they rush in with their army, given that they have this slight advantage based on timing. So this requires coordination between the strategy, tactics, and scouting competencies. Another example is diversion attacks, where you actually have to know how much information your opponent has about you in order to place your army to know how to draw their forces away. So you have to manage information between